we're going to talk in a little more detail about these notations we used when we talked about areas and distances. So this idea of what's called a definite integral is this notation right here. So as we did in section 4.1 when we were approximating the areas under the curve, we divided our subinterval AB into n subintervals of equal width, which we were calling delta x. Delta x is just the length of your interval, which is b minus a, divided by the number of subintervals. We use this notation x0, x1, x2, up through xn. And x0 was a, the first number in our interval, and xn, which was the b, was our last number in our interval. And these x1 star, x2 star, xn star that you saw in the previous section, those are just sample points. If you remember at the beginning of 4.1, I started by just kind of picking random points within each subinterval to give me the function value that was the height of the rectangle. So all you need to know is that these xi stars are somewhere in the subinterval xi minus 1 xi. And so we call the definite integral of f from a to b this. This symbol here is the integral symbol. Integral from a to b of f of x dx is the limit as n approaches infinity of the sum from I equals 1 to n of f of xi star delta x. In other words, the approximation of your choice, which is represented by this sum, if we take infinitely many rectangles, that gives us the exact area under the curve. And the area under the curve, we're calling that the definite integral of the function from a to b. So if this limit exists, we say that the function is integrable on ab. Putting this into perspective, think about what we've talked about in this class up to now. We talked about this really important thing called a derivative, which the notation for that was f prime of x, and the representation for that was slopes of tangent lines. What that meant was slopes of tangent lines. Now we have integral of f of x dx, and what is the interpretation of that? Well, as we've been saying, this integral is the area under a curve. So that's the main interpretation, area under a curve. I'm going to put the word under in quotation marks because something interesting happens when our curve goes below the x-axis. And we'll definitely address that by the end of this section. If we have a continuous function f on an interval ab, or if there's only finitely many jump discontinuities, remember a jump discontinuity was something like this, where it goes and then it jumps up and then it jumps up to something else. It could jump down too. If you have finitely many jump discontinuities, or if the function is just continuous all the way through, then the function is integrable. In other words, the definite integral exists. And again, here's just a review of the notation that we mentioned in the previous slides. The xi, the systematic way to define each xi, is a plus I times delta x. What we're going to practice right now is taking one of these limits of sums and interpreting it as an integral. Okay, so how do we write this as an integral? We know that this limit is going to equal the integral from something to something of some function dx. Well, when you look at it, the function that we're integrating is probably this one without the subscripts of I. So that's one thing we know. This is going to be integral of x cubed plus x sine x dx. But we're not done yet because we need these numbers here, which we call the limits of integration. So what are the limits of integration? What's the a and the b that went on the integral? Well, remember the endpoints of our interval are a and b. That means the limits of integration will be 0 to 2 pi. And that's it. All we were asked to do in this problem is express this as an integral. Remember, this symbol is the integral symbol.